Hello, good morning, everyone. Okay, so welcome back after the mid-semester break. All right, so I hope you all saw the announcement so far. All right, so the first thing is the lab demo. I've extended it by 1 more week. All right, so that is to give time for those of you who have issues with the ESP32. All right, and yeah, so generally the board I think is fine. Usually it's the cable that is the issue. All right, so if you have problems, try to check with try different cables and see which one works. Okay, but if you still suspect the board is the issue, you can always do a swap, all right, and then try out until you get a board that works. Okay, so that is the first announcement that I sent last week, and the other one was for the midterm. Okay, so later I'll talk about that towards the end of the first set of slides over here. All right, so basically before the mid-semester break, we have covered all the hardware related stuff. Okay, and I think all of you have also done your part in the labs, all right, from those times that I walked around and I saw. So all of you have really tried your best to do what you can and put things together, which I think is good. And the whole objective of the lab demo is to actually give you the very high level of confidence that actually you can put everything together, okay, and you can see it working. All right, and I believe that once you do the lab demo, all right, at least you already achieve a level of functionality where you see everything coming together. Okay, you will automatically be more motivated to actually build up the rest of the hardware and the software. Okay, because once you are able to show that you can use your app or some web UI to send data across the ESP32 to the KL25Z, okay, then you will automatically want to extend that. Okay, so instead of just controlling the RGB LED, now I want to control the motors, I want to play back audio, I want to control the running lights and so on. Okay, so then it's just a matter of how within your team you break up the workload. All right, who's going to do the hardware, who's going to do the device drivers for the various subsystems and putting things together. Okay, so again, as long as you work consistently over the next few weeks, I'm very sure that you can put everything together. Okay, so what we are going to be starting off from today onwards is the OS part. Okay, and we are going to understand the overall idea of what is an OS, why we want to have the OS. All right, and so why you want to have the OS, I think we will come back to that a bit later after we learn some concepts. All right, so in today's lecture, we're going to get introduced to the main concepts, okay, of OS and tasks, and I'm going to go through this week's lab. All right, and by going through this week's lab, you also sort of cover a lot of the similar discussion points in the tutorial as well. Okay, so I think it's sort of very nicely placed together. Okay, so if you understand this lecture, all right, then the core concepts are clear. Then subsequently, we will be learning about more also more advanced techniques of how to manage a multi-threaded environment. Okay, so let's go ahead and get started over here. Okay, so we're going to go ahead with lecture 9, which is the introduction to the OS. Okay. So in terms of the OS, we're going to understand things like process management, memory management. Okay, so one of the last topics we'll be covering is this concept of virtual memory. All right. So in terms of OS, there's two main things. One is, of course, managing multiple tasks, okay, or processes. All right. The other one is how to manage the memory. Okay, so in terms of that, there are a few components to it: how memory is allocated, how we protect it, and the concept of virtual memory. Okay. So these are two main things that I would say we will cover. Now, these other things, all right, like file systems, IO, network, and so on, these are all sort of additional OS components that are generally supported by most operating systems. Okay, so if you take any operating system, they will already have a sort of a low-level API or driver to support either files or IOs or networks and so on. All right, so basically what the OS does is not only does it allow us to create sort of a multi-threaded code base, it also allows us to access the underlying resources using the OS framework. Okay, so the OS itself sort of encapsulates everything and gives us all the necessary APIs or sort of drivers to manage what we want. Okay, so that is the advantage of OS. Okay, now what is a process? Okay, so this concept of process, I think we should clarify from the very beginning, because when you look at reference textbooks or do some research online, you will come across three different terms. Okay, one is process, the other is called task, the other is called thread. Okay, and what has happened, okay, over the years is actually people have started using all these terms interchangeably. All right, so some call it multiple processes, some call it multiple tasks, some call it multiple threads, and so on. Okay, so it has become sort of a loose term. All right, and if you go and do some search, okay, for what is the definition, one website may say something, another website may say something else, and so on. All right, so the general view is they sort of represent similar concept. It's just how you want to define it. All right, so one possible way, okay, so I mean, I'll just give you one possible way of defining it. Okay, you can think of process as something as a higher level sort of activity you want to carry out. Okay, take for example, you launch your YouTube application. Okay, so you launch a YouTube application, so that is itself is a process, okay, that is running on your OS, okay, whether it's a handphone or whatever. Now, for that process to run effectively, I need to manage many activities, correct? So I need to manage my sort of video data, okay, the picture, the pixels and all of those. Then I need to manage the audio, okay. Then I need to manage the user interface, and then I need to also keep track of the network data. Okay, so I'm just giving you a very high level overview. There could be many other subtasks and so on. Now, these sort of activities that are related to this higher level process is what generally we call as threads or tasks. Okay, so I have a higher level process that I want to run, and to make this process run effectively, you have multiple threads or tasks. So we call it T video, T audio, task UI, task network, and so on. So each of them will have to run, okay, to manage different aspects of the process. Okay, now the good part of moving towards this multi-threaded environment, okay, is that when we write all these tasks, okay, the mindset will change. Okay, that means until now, all right, even in the first half of this module, generally we have been thinking in a very sequential manner. All right, if you take for example, you are correct, you program this register, you enable this, and then you wait for the flag, you read the data, and so on. Okay, so the only thing that is sort of not in sync is when you have interrupts. Okay, but besides interrupts, generally we say that everything sort of flows in sequence. Okay, so we have a predefined order of doing things. But when you go to this multi-threaded environment, you no longer have this concept of sequence, because what happens is you will now write code with a very different thinking, that each task is actually focused on a particular activity without much concern about what is happening elsewhere. All right, that means when I say I write task T video, I'm focusing on making sure that the data that is related to the video display is handled correctly. When I run a task T network, I need to make sure that the data packets are arrived correctly, and whatever error checking and correction, everything is done while I'm receiving data to the network. Okay, so each task that you write is going to be written for a very specific purpose without bothering about what anybody else is doing. Okay, but of course, we know that in reality, even though we have individual tasks sort of mindset, we know that still it's all linked together. All right, that means eventually the video and audio must still sync up. All right, if not, your video will play and audio will come either earlier or before, earlier or later. All right, so there has to be some synchronization. Okay, at the same time, the video and audio should only be able to display or produce an output if the network has received the data packet correctly. So there must be a way for the network, okay, to send some signals over to the T audio and T video to say that, okay, now you can process this and so on. Okay, and similarly, the TUI must also be able to have some overall control. Right? And if I want to stop playing, I must be able to tell the network, okay, stop receiving data, okay, stop playing back, and so on. Okay, so the thinking will now change. All right, you will now write tasks with specific actions in mind, but at the same time, you will also learn how the different tasks can talk to each other, can synchronize, and sort of manage the flow. Okay, so the whole process and thinking will change, but you will realize that even though the initial sort of transformation from a single threaded to a multi-threaded can be a bit of a challenge, but once you move in this direction, you will also see that your life becomes a lot more easier when there are changes. All right, so once there are changes in the system, all right, you will realize that it's a lot more easier to handle the complexity compared to if you were running it in a single threaded mindset. All right, so that is the sort of general idea, okay, of moving towards this multi-threaded environment. Okay, and again, what we want is we want to abstract the process and break it down into multiple tasks. All right, and at the same time, you can also have multiple processes running the same program at the same time. Okay, so an example of this is, for example, when you open up Microsoft Word many times. Okay, each one is own document, but still there's only one Microsoft Word installed. All right, but each time you activate Microsoft Word, it opens up. It is a new instance of that same application. All right, with its own sort of memory space, dealing with its own document, and even though everything is open at the same time. All right, so it's possible, correct, to also open up multiple instances of a similar program with the same code base, okay, using the process or the multi-threaded process architecture. Okay, so these are some of the things we will be covering, okay, how to create, how to schedule, and so on. Okay, then of course, in order to make sure that everything is managed correctly, we also need to make sure that the memory is well managed. All right, so when I launch a process, so for example, like in the example where I have two Microsoft Word applications open, I cannot allow one Microsoft Word go and affect the data from another Word document that is not open currently. Correct, so it has to be within its own private memory space. Okay, so I need to protect that data. Okay, but at the same time, there are things that are being shared. Correct, because Microsoft Word is a single application. So a single application, correct, but you're opening up multiple instances of it. Okay, so how do I manage this? All right, so these are things we will talk about. And we also talk about virtual memory. How do I increase the memory that I have virtually, okay, to support more processes being managed by the system. Okay, so files and IO, again, like I said, these are things that are supported in general by the OS. Okay, so if you want to create files and do some file management system, you can look at what is provided. In terms of IO, in our project, we ourselves are writing our own device drivers. So all the stuff that we worked on in the first half of the semester, the LEDs, the motor control, the UART, everything is now part of our IO device driver framework, okay, which you will use in your project. All right, so one of the main things about operating system is how do you come up with the overall structure. Okay, so because you have many different tasks talking to each other, okay, and it's not so straightforward, okay, to think of how to organize a project. Correct, so generally most software can become very complex. All right, and if you go back to a single threaded environment, you realize that as you work on your code, what happens is there's always this issue of extensibility. All right, I think reliability, backwards compatibility, maybe you still may not be able to relate to it so much, but extensibility is always an issue. Okay, so what do we mean? Okay, so for example, right now, if I say that, let's say we never use OS, okay, and you'll have everything as a single threaded environment. Okay, so I send data over, my robot will move forward, okay, backward, and so on. And you run everything, it works. All right, and of course you have your LED, and somehow you manage to figure out all the exact timing, and you do everything correctly, okay, using a super while loop. Okay, but the moment something changes, correct? So if I say that, okay, while my robot is moving, I also not only transmit data from my app to the robot must be able to send some data back to another computer, okay, using Bluetooth or using Wi-Fi. I add something else, okay, or I add some other new sensor at the front, okay, or I add another servo motor or a LiDAR or something like that. So the moment I add something or I change something, okay, the whole system will break, okay, very easily, because the timing relationship between all the different tasks you've written would have changed. Okay, so that is one of the main reasons why the OS is actually very powerful, because I can very easily extend or reduce the functionality without impacting the behavior of the system. Okay, so you see how sort of how powerful it is, all right, when you want to make it more complex or even make it more simpler. All right, so the whole idea of a real-time operating system. Okay, so the main difference between operating system and real-time operating system is basically this keyword here. Okay, so what is real-time? So when you say real-time, okay, there's two things to it. One is predictability, and the other is determinism. Okay, predictability means I can guarantee you. Okay, I can guarantee that if I press this particular button, okay, this particular LED will light up. Okay, so I can always be very predictable about how the behavior is going to be. Okay, so that interface or how the data is processed is always consistent, and it's deterministic in the timing sense. That means I can always guarantee you and say that if I press a button, the LED will light up, okay, within 100 milliseconds, okay, or 50 milliseconds. So I can always guarantee you a particular response time. All right, so another sort of common misconception that most people have is real time equals to fastest response. Okay, so the answer is no. Okay, the real time is not equal to fastest response, because real time basically means you are able to meet the deadline. How much or how long is the deadline is up to you or the system requirements to be defined. But if I say that if I press the button, the LED must light up within 1 minute, then 1 minute is my deadline. As long as the LED lights up within 1 minute, I still say it's a real-time system. Okay, because the concept of time is very subjective. Okay, it all dependent on the requirements of the project that you're working on. Okay, so whether the deadline is 2 milliseconds, 2 minutes, or 20 minutes, okay, as long as you have a timing deadline and the system can meet the deadline, then you say that you are able to fulfill the real-time requirements of the system. All right. Now another thing, okay, which we probably are not going to implement it, okay, but it's something that you should think about, especially if you are having some idea of creating a startup company and you want to create your own product or something like that. How do you make sure your product is fail safe? Okay, so this is a very important thing, okay, because many times, okay, of course, as students, we focus on the functionality and fulfilling all the requirements, that we are assessed on and things like that. Okay, but of course, beyond school, okay, when you talk about a product that you want to sort of commercialize and ship out and things like that, you need to always factor in the chance that when the product reaches the customer, it may fail. Okay, either fail on startup, okay, or put out on the system, or halfway through using it may fail. So if it fails, how do you ensure that it can fail safely? Okay, so fail safely means you must be able to make sure that you put everything in a proper state before you are able to shut it down. Okay, so again, this depends on the kind of system you're dealing with and what are the sort of actions you must take before you shut down the whole system. All right, so again, these are things that you need to think about. Okay, some real world examples I will talk about. Okay, towards the end of the module. Okay, where we have covered everything, and then we're going to talk about some of the historical sort of talked about issues with OS being deployed in the field. Okay, now another common term you will see is embedded operating systems. Now again, this is another term that has also been loosely linked with RTOS. Okay, so generally embedded operating systems and real-time operating systems are, in a sense, even though they are not exactly the same, they are used interchangeably. Okay, and why is it so? Because generally an embedded system, okay, is either you have an OS or you don't have an OS. And simple systems generally don't have an OS, correct? Like if you take a simple, like a remote control, okay, whether it's your TV remote or your aircon remote or things like that, those are very simple systems, okay? Basic input, basic output. All right, you can easily implement it with any controller, so you don't need an OS, okay? But the moment you talk about a more complex system, okay, like a MP3 player or a GPS, all right, then you may want to have OS, all right? And generally, most embedded operating systems out there in the market have some real-time capability. Okay, so because of that, people have generally used these terms quite interchangeably. Okay. So again, the whole idea is we want to move away from the super loop. Okay, until now we were always having this super loop, okay, a big while one loop where everything goes in sequence. Okay, and if you recall our one of the earlier lectures where we talked about the pothole detection system. All right, the moment some dynamics changes, all right, the whole flow and the whole timing will be affected. All right, so the only way to make sure that it is as deterministic as possible is to again, interrupts is always a possibility, but there are always a limitation on I mean, there's always a limit to how many interrupts your system may support. Okay, whereas with multitasking, all right, you have no limit to how many threads you want. Okay, basically, as long as you have enough memory in the system, you can create as many tasks as you want. Okay, and using a multi-threaded environment, you have a lot more flexibility in the overall software architecture, okay, of the whole system. Okay, so for this module, we are basically using the Keil RTX, okay, the Keil RTX OS. All right, so it's a very well-known OS that supports the ARM MCOS. All right, and is well sort of suited for RTOS, for embedded systems. And the API that we'll be using is what we call the CMSIS RTOS API. All right, so this is a higher level lot of a library that will call all these functions over here. Okay, so when we are doing the lab, you sort of see how it comes together. All right, and we'll make use of these APIs to make use of the Keil RTX. Okay, so before we go on to the next set of slides, I just want to do a quick poll to understand how is your hardware development coming along so far. Okay, so more and more people are asking what hardware. So I hope it's just for the fun of it. All right. Again, I've always reminded you, time flies very fast, especially in the second half. Okay. I still remember, I think it was 2 batches ago, there was one group that came on the last Friday, and then that's the first time we opened up the chassis to fix up the motor and the wheel. Okay, so you probably know what happened to the project. All right. So I hope I don't see that happening. Okay. Again, as long as you manage your time, you should be able to do it. All right. So all your device drivers have already been developed, all right, over the weeks. Okay. So what is left is actually putting things together. All right. Even though we are only starting OS, even before that, you can already put everything together right now. Okay. And like I said, once the demo framework is already done, okay, if the hardware is ready, you can immediately, okay, just using the single threaded environment as it is right now, you can already control your robot. Okay, you can already control your robot. Okay, once you see that happening, you will be a lot more, you yourself will feel good. Okay, and trust me, once you see other groups doing it, you will feel more pressurized. Okay, so the faster you get the hardware up and running, I think you will be a bit more relaxed, and then you can just focus on the software aspect of the whole system. Okay. Okay, so let's okay, so let's move on, okay, to the next set of slides, which are processors. Okay. So give me a minute here. Let me... Okay, so let's go to the next set of slides on processors. All right, so again, processors or tasks or threads, again, the idea is the same. All right, so whether you think of a high level activity as a process and you call it multiple sub processors or tasks or threads, the idea is the same. Okay, so we're going to look at processors and how it works, and we're going to look at some RTX examples. All right, and then from there you will understand the very important concept, which is the context switching and the states. All right, so this is very important because we need to fully understand how the multiple tasks that we create are actually managed by the OS. Okay, so what exactly is a process? All right, a process is basically an instance of a running program. Okay, just like how, for example, if I open up the Keil Microvision, okay, multiple times with different projects, I will create multiple instances of it. Okay, so the OS is managing it. So when it creates one Microvision instance, it opens up one project, then another, and another, and so on. Okay, and each of it has its own memory space, has its own sort of utilization of the CPU, and so on. All right, and there is no issue that the same Microvision is running different projects in different instances. Okay, because the OS is able to manage all the underlying resources correctly. All right, so that is the whole idea of a process. That means I create an instance of a particular running program. Okay, so when you create this process, okay, if I have multiple Microvision or multiple Microsoft Word or whatever, what do I need? I need to be able to make sure that I able to allocate some CPU time to each of these processes. Right, just like right now on my PC, right, I have my PowerPoint running, I have my Zoom running, I'm connected to the network, okay, my camera is functioning. So I have multiple processes that are running, all right. So each process must be able to have some CPU time allocated to it in order to perform what it's supposed to do. All right, so that is the role of the OS. The role of the OS is to make sure that all the tasks in the system are able to have some proper CPU time allocated. Okay, so at the same time, when you for your CPU to execute, you also need memory, right? Because you need to hold the software, the execution program, the data, the variables, and so on. So you need some memory. All right. And since I have so many processes running, I need to be able to keep track of the process. Okay, so there's a process ID that has to be allocated to each instance. Okay, so even though I open multiple Microvision application, each of them will have its own process ID that is managed by the OS. Okay, and within the process, I may also need to create multiple threads. Okay, so these are the main things that a processor needs in order to be able to effectively execute on your system. All right, now when I create a process, is it aware that there are other processes? All right. So one is, okay, the operating system role is to create this illusion that a process has everything that it needs to be executed. Okay. So when you open up your browser or you open up your Microsoft Word or anything, okay, the browser will behave as if it is owning the CPU. All right. You never see a case where you type in a web address, okay, in the address bar, and then when it's trying to load, it says, "Oh, I'm sorry, I'm busy with the Microsoft Word. I'll come back later." No, okay. It always gives you the illusion that if I'm currently using the browser has full access to everything, the CPU, the network, everything. If I switch over to another browser, then that browser will behave as if it owns the CPU. So every process gives us that illusion, okay, that it actually owns everything and is able to do everything that we want it to do. Okay, so it does it because the OS manages it in that way, and at the same time, it's also able to create an abstraction of the hardware resources. Okay, so multiple processes may require the monitor, the screen, the keyboard, the mouse, everything. But at any point of time, whichever process is active will get to use it. Okay, so every process sees one dedicated processor. Okay, even though the processor is being shared, okay, the whole memory is being shared, the process itself has this illusion that the processor is dedicated to that process alone. Okay, similarly, the memory, okay, though you have a lot of memory, you have one portion already set aside for that particular process. Okay, of course, there are techniques to allow processors to talk to each other, which we will also explore later on. Okay, but we will look at it more from the inter-task communication. All right, so what is the memory layout of an executing program? Okay, so I'm just giving you an introduction here only. Okay, there's one more topic later we'll cover on where we'll go through this in more detail. Okay, but generally, okay, the code that we write, okay, will be compiled into, eventually when we click on the compile button, we go to assembly language, and then finally the binary code. Okay, and that binary code is basically stored in the what we call the code section or the text section of the program. Okay, and then you have some data, and the data is generally broken up into what is initialized and uninitialized. All right, so there'll be one set of data that is initialized. That means you already declare it some initial variables, values. All right, and then some data you just declare a variable, but you do not initialize it. All right, so they'll be allocated to do different sections of the memory. Okay, and besides that, you have your stack and your heap. Okay, so stack is used whenever you have procedural calls, okay, to keep your register or your return values, your temporary data, and so on. Then heap is when you do some malloc and free. All right, so this is the general overview. Okay, there's one lecture later on. All right, further down where we will go through this in more detail to understand these various sections. Okay, so in terms of the process, okay, I think the key idea is that the process, okay, multiple processes that are running will actually switch between themselves, all right, through the OS. All right, so right now, okay, like now I'm showing you these slides. All right, but at the same time, my Zoom is running. All right, my camera is working. All right, everything is working correctly. All right, because the OS is able to keep track of everything that is going on, and is continuously switching between various tasks. Okay, to make sure that the requirements of each task or each process are managed correctly. All right, so that is what we call the abstraction of the process. All right, and this is what I mentioned just now. Okay, the sort of I would say the loose definition of process, task, and thread. Okay, so in our module, I will just say that we generally can use them interchangeably. Okay, so whether I call it process or call it task or call it thread, it's still the same idea. Correct. So it's still the same idea. A high level task can be broken down into lower level tasks and so on. Okay, or you can call it a high level process breaking up into multiple tasks. Okay, it's the same concept. All right, so when I create a process or when I create a task, all right, the OS also creates what we call a process control block or task control block. So what is this task control block? Okay, this task control block basically contains all the information related to that particular process that the OS needs in order to manage it. Okay, so what is the process ID, the state, all the registers and memory and so on. So all the information related to that particular process is stored within that process or task control block. Okay, so this is an example of a task control block. All right, so this is again managed by the OS. So the moment I create a new task or a new thread, okay, you will see that, okay, it automatically creates all this information for you as part of that task. Okay, so of course it has a lot of information, but the three important things is what I highlighted here: the state of the task, the priority, and the task ID. Okay, now let's look at the various states of the task. Okay, the various states of the task. Now, when I first create a task, what happens is the OS will allocate a unique ID for me. Okay, now do I need to know this ID? In some parts or in some APIs that you'll be using, you need to know the ID. All right, so this ID is usually returned. Okay, it's a return value when I create a task. Okay, so I will show that later. Okay, and while the ID is also allocated, it also does the allocation of the memory, okay, for the process control block as well as the memory required by the code. Okay, then it initializes all the process control block and the memory related aspects, okay, before it adds it to the queue. All right, now when I terminate a task, okay, let's assume you create a task and now you don't need that task anymore. All right, so in some cases you can stop the task, in some cases it may terminate itself. Okay, why would you stop a task? Okay, basically because you no longer need it. All right, or maybe itself is giving some issues, so you just want to end that task, just like how we end a process or end an application in our PC. All right, you can also do that in any system. So generally, once you end a task, you want to return everything. So you release the resources, okay, that were originally allocated to you. All right, and after that you are able to free up the memory. All right, so the idea of terminating a process is quite familiar to us, correct? Because in the PC we always do that, okay, or even in our handphone also we do that. All right, we can choose to permanently stop some of the apps from running. Okay, but in an embedded system, okay, generally we don't say that processes terminate. Okay, in embedded software, generally what we do is we create all the processes we need and ensure that if I need any of the processes to run, then I put in that framework that is necessary that a process will be able to wake up and perform the action when needed. Okay, so when I create multiple processes, okay, it doesn't mean that everything will run. So I may create task 1, task 2 up to task n. Okay, I may create 10 processes, 100 processes, doesn't matter, or 10, 100 tasks. Okay, it doesn't mean that all the tasks are now going to be running and competing for the processor. No. Okay, I can create a task and yet I can choose to put it in a state there where it will not use the CPU. All right, and only when needed I can sort of activate it to perform some action. All right, and then it may again go back to this sort of state where it doesn't use the CPU and only gets reactivated when the next requirement comes through. Okay, so when I have so many tasks in the system, all right, okay, and the OS needs to keep on switching between the different tasks. All right, so this switching happens very, very fast. Okay, in matter of milliseconds, okay, a task will switch from one to another and back and so on. Okay, so this switching between one process and another process happens very, very regularly in the background. So we do not know this happening. Okay, we do not see it happening. So the OS is managing this for us. Okay, so that is the main reason why everything seems to be working very well. Okay, because even though I have a single processor, okay, the OS is actually switching very quickly between all the different processes to make sure that everybody gets the ability to use the CPU for some fraction of time. Okay, and then be able to execute, and then the next, and so on. Okay, so since this switching is happening all the time, I always need to keep track of where I was in each particular task or each particular process. So that is where the process control block comes in. Okay, so when I'm switching, okay, from one task to another task, so I want to go from A to B, I first need to save the context of task A. That means save the current state to the process control block of task A. And since I want to run task B, I need to restore from the process control block of B. Okay, and once I'm done with the execution and I want to go back to task A, I do the reverse. So I save the state of process control, save the state to process control block for task B, and restore the state from process control block for task A. All right, so this is happening very, very fast. Okay, very, very fast in the background. Okay, so it does consume some time. All right, but generally, because the processor is running at a very high sort of frequency, okay, we don't really feel the effect so much. All right, and of course, it has its own resources to manage and do this effectively. All right, so now comes to the key thing, which is the process state. Okay, so when I say that I'm continuously switching between the different tasks, okay, different tasks, okay, that means the tasks could be in different states, okay, at different times of my execution. All right, now this task states have many different variants. Okay, so in this particular RTX RTOS, it is defined in 5 different states. If in the future you pick up another OS that you want to look at, you may have different states. Okay, so those of you who have is maybe the first time you are dealing with OS, if you are keen to explore, okay, because you want to do something else on your own and so on. All right, one other OS you can explore is called the free RTOS, and the free RTOS runs on the Arduino Uno. Okay, so you have a Arduino Uno on your own, you can actually directly run free RTOS on it. Okay, so that is another OS you can also try, okay, on the Arduino Uno board. Okay, so there are a lot of other OS in the market. All right, some are free, okay, like this free RTOS, some are paid. The one that we're using is free up to a certain size limit, which is more than enough for our project. Okay, so of course, you want to develop more complex applications, then you probably need to have a license. Okay, so let's look at the different states. Okay, so the state that we are looking at, all right, so if you see, these are the 5 different blocks here, okay, that we want to fill in. All right, and we want to fill in based on understanding of what happens at each stage of time or each state of time. All right, so the very first state is what we call the new. Okay, that means you are creating a task for the first time. Okay, when I create a task for the first time, what will happen is the OS will allocate, okay, like we said, you will allocate yes, you will allocate the memory, initialize the process control block, and add it to the queue. Now, what is this queue? Okay, what is this queue? This queue is what we call the ready queue. All right, so the CPU, okay, we only have one CPU. All right, but at any point of time, I can have many tasks being created in my system. Okay, so I can create task 1, task 2, task 3, and so on. Okay, so there will be a queue here waiting, all right, to make use of the CPU. Okay, so I can have a queue here, and I can say task 1 is first, task 2, and then task 3, and so on. All right, now when I have tasks that are in the ready queue, so when you say ready means what? When you say that a task is ready, it means that it has all the resources it needs to actually execute. That means it is ready and waiting for its turn to execute. Okay, so it's waiting for its turn. And who is going to decide? Okay, so that is where another important element in the OS kernel comes in, which is called the scheduler. So within the OS, okay, we have this sort of manager which we call the scheduler. Okay, and the objective of the scheduler is to look at this ready list and select the next task to run. Okay, so of course the list is very dynamic. Okay, it can continuously keep switching, okay, depending on what is happening. Okay, so whoever is next, okay, so assuming that the one at the top of the list is the next, so the scheduler will select the next task to transition from ready to what we call run. Okay, only the task that is in the running state is actually making use of the CPU. Okay, if you are not in the running state, you're actually not making use of the CPU. That means your code is not running. Only one task at a time can be running, and only the task that is running is actually making use of the CPU. All right. Now, when a task is running, okay, there are two things that can happen. Okay, I mean there are three things, but the two main things are: one, it may go back to a ready state. Okay, and that can happen if I choose to give up the CPU voluntarily. Okay, so if I have a timeout. Okay, so if let's say I run for 10 milliseconds, 100 milliseconds, and then I say, okay, I am done, I want to give up the CPU, then I may go into a timeout and I voluntarily give up the CPU. So I go to a ready state. Okay. Now, the other sort of state that I can go to is what we call the block state or wait state. Okay, some references may call it block, some may call it wait, and so on. Okay, but the idea is the same. Okay, so when I say block state, okay, so this is important. What do you mean by block? Okay, when you say your block means you are actually waiting for some resource to become available. Okay, so you cannot run or you cannot continue running because you don't have some resource that you want. Okay, so a simple example I can give you is, for example, your code that is running is the UART code. Okay, you have created a task to transmit some data over the UART. Okay, now you can only transmit if the UART is available. Correct. But what if another task is using the UART, or the task is, or the UART is in some error state that is not yet cleared? So I cannot run anymore, right? There's no point in me holding on to the CPU because what I want to do, I cannot do. Okay, the resource that I want is not available. Okay, so in that case, I can go to a block state. Now, when I go to a block state, what happens? When I go to a block state, what happens is this space becomes free. Right, this space now becomes free because the task that was originally running is no longer running. Okay, so this space becomes free. Okay, so task one was originally here. Okay, so let's assume that task one was running and then it gets blocked. So task one comes here. Okay, so now task one, since it was already removed from the queue and it is already transitioned from the run to the block state, the scheduler is automatically invoked again. Okay, so the scheduler is always keeping track of who is running or who is making use of the CPU and who is supposed to go next. So the moment one of the tasks that is currently running transitions out of the running state, okay, let's say it goes to the block state, then the scheduler knows that the CPU is now free. Okay, so if the CPU is free, it will go ahead to say, okay, let me select another task, the next task in the queue, to take over the CPU. So it will become task 2. All right. Now, when task 2 is running, okay, task 1 is the block state, okay, and then you still have task 3 in the ready state. Now, what happens if while task 2 is running, suddenly the UART becomes available? Okay, so T1, task 1 was blocked. okay, because he was not able to send data because the UART was busy. Okay, now while task 2 is running, suddenly T1 becomes available. All right, so when T1 becomes available, what will happen? Can it straight away go to run? Okay, if you look at the flow of the arrow, you can see that there is no arrow from block to run. It only goes from run to block, and from block you can only go to ready. Okay, so when the task that is blocked because of some resource issue and the resource is now available, what happens is the task will now be able to unblock, okay, and it will transition to the ready state. So task 1 comes to the ready state. So when task 1 comes to the ready state, you will join the queue. Okay, it will join the queue and then wait for its next turn to run. All right, so of course this is a very simplistic view. You still have the concept of priority, okay, because a higher priority task will always take over. Okay, but that idea we will revisit, I think, later on. Okay, for now, let's just keep priority out of it first and assume that everybody is equal priority. So everybody is equal priority. When I get unblocked, okay, I will just join the queue with all the other tasks that are in the same priority as me. Okay, and then again, this whole process will keep on running. Okay, so the key thing you notice is when a task is running, okay, it will run until a point of time where it gets blocked or it goes to a ready state. Okay, and when that happens, the scheduler automatically kicks in to decide who will take over the CPU next. Okay, so there's always somebody who the scheduler will want to choose from the ready queue to run and take over the CPU. Okay, to run, and then when that task transitions out, then the next task and the next task and so on. Okay, and all of this is happening very, very fast. Okay, very, very fast in the background. So you will see as if everything is running in parallel. Okay, but actually everything is running by continuously switching between the various tasks, okay, which is handled by the OS. Okay, so the last block here, okay, this last block here is when you terminate. Okay, so when I release the task, I exit. Okay, but like I said, this part we don't need to worry because in general, embedded based operating systems don't have this concept of exit. Okay, because when the system starts up, you will start up everything. Okay, and then manage it accordingly. Okay, in a desktop environment or in a handphone environment, it's different because you can navigate and you can just start and click on the app and so on, then it will just start running again. Okay, but if you talk about an embedded platform, all right, when you power up, everything will automatically run and then you manage it accordingly. All right, so the last part, even though it is there, okay, it is not something that we will practically use in an embedded environment. All right, so we can sort of ignore that for now. Okay, so the process state, like I said, is about where we are in terms of the view of the scheduler. All right, and there are many different process states. All right, like I said, the ready and running, okay, are the ones that we are focusing on now. So just now I said we generally say that when I'm waiting for something, we call it block, but the block itself actually has a lot of subcategories. Okay, that means I'm blocked or waiting because of, is it a semaphore, is it a mailbox, is it a new text, and so on. Okay, so there are many sort of categories for this, but we don't need to worry about all of this. All right, as long as we understand the concept of what is ready, what is running, and what is blocked, okay, then we can get the flow correct. Okay, so yeah, before we go for a break, I just want to again remind you all of this. Okay, so the midterm will be held in week 9, okay, which is, that means 2 weeks time, okay, in the same lecture slot. All right, so it will be Luminous quiz, is MCQ plus MRQ. Okay, so it's open book. Okay, so you can access any soft copy and hard copy material, but you're not allowed to do any internet searching. Okay, so that means you can open up our notes. Okay, so this soft copy, hard copy material basically refers to all our notes that you have and any documents that you have. Okay, so your PDF files, your data sheet, everything you can open up. Okay, but you cannot open up any browser to do any search. Okay, and at the same time, you cannot open up any sort of programming tool or development tool where you can type code and you can test out the output and things like that. So you can't do that. All right. So lectures will be topics 1 to 10. That means basically up to today's lectures. All right, and then the labs will be up to this week's lab. Okay, and tutorial is 1 to 4. Okay, so the usual stuff I think you all are familiar with, the Zoom proctoring and screen recording, and then we will use the Google Forms for the clarifications. Okay, so all of that, the links and everything, I will prepare the SOP document and I'll upload by this week. Okay, so yeah, so this lecture again, like I said, the concept of what is ready, what is blocked, what is run. Okay, all of this is important. Okay, so you understand what is happening. Okay, so of course, what we covered in theory is best when we see it in practical. All right, so we will go for a break now. Okay, when we come back from the break, we will look at this week's lab. All right, and actually see it in action. And I think that will help to sort of reinforce the things that we just discussed. Okay, so let's go for a break now. It's 11. So 11:10 we'll come back. Okay, and then let's look at this week's lab. Okay, so I'll see you all back here in 10 minutes. If you have any questions, please put it in the chat. Okay, and then I will address them when I come back. Okay, so I'll come back. All right, let's look at this week's lab. All right, so for this week's lab, okay, if you look at your Luminous, there is already a file there. All right, on the lab 6. All right, so you can download the document. Okay, so one of the things is that we have observed in the past is sometimes some of you may have done an upgrade of the environment, okay, the Keil IDE software. All right, and when you do an upgrade, it sort of has some issues with running the RTX. Okay, some of the things will change. Okay, so there is another document further down here that says challenges with running RTX. Okay, so please refer to this document on how you can sort of revert back some of the settings, okay, and the version of the environment that you're using to ensure that there is no issue with running the RTX file. Okay, so how to load the OS step by step, I've already given it in the lab manual, so please follow those steps. Okay, so when you do that and you create your first OS project, okay, you will have something like this. All right, and what you're supposed to do is you're supposed to analyze this step by step to understand what is happening. Okay, so let me explain. Okay, what is happening here. Okay, once we go to a multi-threaded environment. Okay, so when you create the multi-threaded code, okay, you still have your main function. Okay, so this main function, so even if you have an OS, okay, just like how your Windows boots up. Okay, so when you have a Windows and you power up a system, the first thing that will run is actually what you call your BIOS. All right, your basic single-threaded code that will run to set up some very low-level hardware and resources that your system needs before Windows loads. Okay, you can never immediately load the OS. You need to do some initial configuration of your hardware, your resources, your system before the OS can be loaded. Okay, so in a similar sense, okay, when we run it on an embedded system, the main will still run first. Okay, so when the main runs, you need to do some system initialization. All right, so the first thing that we will do is we will call this thing called system clock update. Again, that is just to make sure that the clock is updated to whatever setting we have. All right, so whether it's 48 megahertz or the default or whatever. All right, so this is of course the key thing that we need. All right, to make sure that the clock is updated. Now this two here is just again my own code. Okay, that is because I want to configure the RGB LED everything correctly. Okay, so this is again my own code that is not part of the default code. The default one is the system core clock update which we need. All right, after I do the core clock update, in order to initialize the OS, I need to call this function called OS kernel initialize. Okay, this OS kernel initialize. So what is the OS kernel? The OS kernel is basically the sort of the core of the OS, okay, or the underlying framework of the OS. All right, and you need to initialize this kernel, all right, by calling this function. So when you call this OS kernel initialize, you will go ahead to prepare all the necessary sort of background tasks that you need. Okay, background resources, the tasks, everything that you need for the OS to run correctly. Everything will be sort of done up by this function call over here. So once I initialize the kernel, that means the OS is already ready and available in my system. All right, and once it is available in my system, that means I can actually go ahead to start creating new threads. Okay, I can create new threads by calling this function called OS thread new. Okay, so of course now the first question I ask is, how do I know what to call? Where are all the APIs? All right, so all those APIs are inside this this link over here, okay, which I'll share now in the chat. All right, so if you go to this API here, okay, you can see that I mean this link over here, it lists out all the CMSIS RTOS APIs that we can use. Okay, so under the thread management, if you click on thread management, okay, which is what we are doing now, okay, you'll be able to see the functions associated with creating the function, creating the thread. Okay, so okay, wait, I think that's the wrong link. Give me a minute. So it's under the RTOS 2. Just now it's RTOS V1. Okay, that was the old version. The one we're using now is the CMSIS RTOS 2. Okay, RTOS V2. Okay, so if you go under thread management, okay, under thread management, you will see that okay, you have the OS thread new definition here. Okay, and under the OS thread new definition, you can see that when I create a new thread, okay, what is I need to pass in if I want is the key thing is the function, the actual name of the function that is tied to the thread. Okay, what is optional is if I want to pass in some arguments or if I want to change any attributes. Okay, so for now we are not going to pass in arguments or change any attributes. All right, so the key thing is the name of the function alone. Okay, so in this case we are calling OS thread new, and we're calling and creating this new thread tied to this function called LED red thread. Okay, so when I create this new thread, okay, what happens? That means it is ready in the transition from the new, okay, and it is now going to go to the ready state. It is going to go to the ready state. From the new, it transition to the ready state. Okay, now after I create the task, in order for me to switch from single threaded to multi-threaded, I have to call OS kernel start. Only when I call OS kernel start, I will transition from the single threaded to the multi-threaded. Okay, and once I call OS kernel start, I will immediately switch over to multi-threaded, which means I will not come back to main anymore. Okay, I'll not come back to main anymore. All right, so what is happening? So once I go to OS kernel start, okay, once I go to OS kernel start, I will switch to multi-threaded. Okay, so if I were to look at the timing over here, okay, so first I have my main function. Okay, then I do all the initialization. Okay, initialization, and after that I call kernel start. Okay, kernel start. Okay, the moment I call kernel start, until then, okay, until this point over here, I was still going sequentially. I was still going sequentially. But the moment I call kernel start, I'm no longer sequential. I have now transitioned to the RTOS environment. So in the RTOS environment, who is in charge? Okay, the person who is in charge is my scheduler. Okay, and the scheduler will look at what? The scheduler will look at which are the tasks in the ready queue. Which are the tasks in the ready queue? And in initialization code, I already created, okay, a task called LED red thread. Let's see what is the name that I use, LED red thread. So I've already created this. So since I already created this with the new function, OS thread new function, that means this, okay, I'll call it red, okay, has already joined the ready queue. So if I look at the ready queue, I have already, I now have a task which is the red LED in the ready queue. Okay, and what the scheduler will do is it will look and see that, okay, I have a particular task which is in the ready queue, all right, and there is no other task that is running the CPU at the moment. So I will take this task and I will transition it to the run state. So the red LED task will go to the run state. Okay, so that is basically what will happen. Okay, so when I run this code, okay, what will happen is the moment I call OS kernel start, you will immediately switch over to the multi-thread environment, and you will see that this thread is currently created, is in the ready queue. So I can now transition that task to the run state. Now let's look at this task. So in this task over here, what is happening? Okay, so let's look at the code over here. Okay, so here got two tasks, but you just look at the LED red thread alone. So in this LED red thread task alone, what is happening? You will see that firstly, it is written in a infinite loop, for loop. Okay, it's written in infinite loop, and inside that loop, I do some activity. All right, so this is again something different, right? Because you in our normal single-threaded environment, we never write an infinite loop inside a function because we know we'll get stuck there. Correct. So we do not do these kind of things in a single-threaded environment, but in a multi-threaded environment, we will write every task as if it is running by itself. Right? That means it has a CPU to itself. So because we have this mindset that the task is going to hold the CPU to itself, we want this task to run forever. Okay, so that is why we have a forever loop, okay, or while one loop. Okay, so in this while one loop, okay, what am I doing? So first I call the LED on, okay, and after I call LED on, of course, this is my own code, so I'll light up the LED, and then I call this function called OS delay. Okay, for 1000. So what is OS delay for 1000? Okay, so let's look at that. Okay, so if I go back to my documentation here, under OS delay, you can see that it calls, okay, it allows, okay, for the current thread to be put into a block state, okay, for the amount of ticks. Okay, so for now we will take it that one tick is approximately 1 millisecond. Okay, approximately 1 millisecond. That means when I put 1000 ticks, it is approximately 1 second. Okay, so what will happen is when I call OS delay with 1000 inside this parameter, 1000 ticks, that means 1000 millisecond, I will put myself into a block state. Okay, I'll put myself in a block state for 1 second or 1000 millisecond. Okay, and as we saw just now, when I come out of the block state, I will go to the ready state. Okay, and then after that, again, it comes back to the scheduler. So the scheduler will then decide from the ready queue whether I need to run or I'm able to run again. Okay, so if I come back with that same understanding, so what is happening? Okay, so if I were to draw the timeline over here, so let's say this is my LED red function. Okay, so at the very first instance, what I will do is I will say on the LED. Okay, so on the LED. After that, I call OS delay for 1000. Now, the moment I call OS delay, so until this point, from the time all the way to here, I was in the run state. Okay, but the moment I call OS delay, what happened? I will transition to the block state. Okay, for how long? For 1 second or 1000 milliseconds. So I'll be blocked for 1000 milliseconds. All right, so when I am blocked, okay, at this point of time, what happens? Okay, so I come back here. What will happen is I will go to a block state. Okay, so the red LED will transition to the block state for 1000 milliseconds. So once my red LED transition, then what happens? My run task, there's no task in the run state, which means that my CPU is free. Okay, so if my CPU is free, I would be able to allocate some other tasks to actually run and take over the CPU. But in our case, currently there is no other task. There's no other task, so the run is still empty. That means there's no other task that is going to take over and run. Okay, and this task is going to be blocked. Okay, now when I finish my 1000 ticks or 1000 millisecond, what happens? Okay, as we saw in the documentation just now, it will come out of the block state and go to the ready state. So at this point of time, I will transition to the ready. Okay, I can never go from block to run. I can only go from block to ready. Okay, because the timer has elapsed. So after I go to ready, then what happens? Again, the same thing happens. Okay, that means from here, I am now going to take my task and put it back in the ready queue. Okay, but it just happens that there's nobody else in the queue. So I'm still the first one in the queue. Okay, so since I'm in the first one in the queue, the scheduler sees that now I have a task in the ready queue. Okay, and the CPU is free because nobody is in the run state. I will again transition my red LED back over here to the run state, which means I will be able to execute the off of the LED. Okay, so once I come here, there's nobody else waiting, so I can transition to the run state. Okay, so nobody else in the queue means I can transition to the run state. When I go to the run state, what will happen is I will off my LED and then call another delay 1000. Okay, and it's the same thing. So the whole thing will keep repeating itself. Okay, so once I call delay 1000, okay, so the run is until here, and once I call delay 1000, I will go to the block state. Okay, so that is basically what is happening here. So even though it seems like a very simple code, actually a lot of things are happening in the background. Okay, because the scheduler is involved, the task switching is going on. Okay, and all this transition is happening in the background. Okay, now let's see this in action. Okay, so let me bring out let me compile the code here. Okay, so now if I run my code, okay, you'll see that the red LED is blinking. Okay, so this blinking again is not the same blinking as we saw in the single threaded environment. Okay, where we just have a normal delay. Okay, this is using the OS and using OS delay. So all this context switching that we just discussed is actually happening right now. Okay, in the background. Okay, so that is what the or how the code is executing. Now, if I put a breakpoint, okay, so let's assume that I put a breakpoint here. Okay, what you notice? You notice that under here, even though I only created one thread, LED red thread, there is something else here created as well. One is the RTX timer thread, the other is RTX idle thread. All right. So this idle thread is another thread that is created by default. Okay, why? Because in the event where I'm not running anything else, okay, then the idle thread will be running. So that is telling us the system is still alive. Only thing is it's idling. There is no other task actually occupying the run state of the CPU. Now the timer thread is there. Again, is something created in the back end to manage all the context switching that is going on. Okay, so the RTX idle thread and timer threads are things that are created in the background the moment you call OS kernel initialize and you call OS kernel start. All right, so those are not created by you, but they're created by the system. Okay, the LED red thread is what we have created, okay, in our by ourselves. Okay, so if I remove the breakpoint and continue, so you'll just continue from where you left off. All right, so this is basically what you would observe in the initial code that you run. Okay, so of course, this is just one LED blinking. All right, now let's extend the code a bit. All right, so the same thing. Now I'm going to call OS thread new for two LEDs, one for the red, one for the green. Okay, one for the red, one for the green. Okay, and both of them have exactly the same code. Okay, you can see here, both of them have exactly the same code. The red LED thread and then the green LED thread. Okay, so both of them are exactly the same code, and I'm going to call it in the sequence here where I create red LED first, followed by green LED. Okay, now before I compile and run this code, okay, let's do a poll first to see what you think will happen. Give me a minute. Okay, so let's do a poll to see what do you think will happen. All right, so as what you saw, the two tasks are the same. All right, and both of them are created in sequence. The red LED one is created first, followed by the green LED. All right, so what will happen? Okay, so I think most of you feel that both will be on, both will be off. Okay, some feel that it's red first and then the green. Okay, some only believe it's going to be the red. Okay, so let's clear this and let's come back. Okay, let's come back to our code. Okay, so let me compile this and run it here. Okay, so if I run it now, okay, so Russia, you guys can see clearly on your screen, but it's basically yellow. Okay, so yellow is basically red and green together. Okay, red and green together will give you yellow, which is what I'm currently seeing on my board over here. Okay, so why is it yellow? Okay, why is it yellow? Because okay, so let's come back to this again. So now we have two threads, correct? LED red, LED green. Okay, so what is happening is since the red one was created first, okay, since the red one is created first, the red one is going to join the queue first. Okay, so when the scheduler looks at the queue, you will see the LED red to be the first one in the queue. So the LED red will come. Okay, so it will do the first step, which is I will switch on the LED. And after I switch on the LED, I will go to a delay. So we know that once I go to a delay, I'm actually going to be blocked. I'm going to be blocked, okay, for 1 second. All right, so the first thing that you must understand is until this point, okay, we can say that while LED red was running, LED green was still in the ready state. So we were still over here in the ready state. Okay, but the moment my LED red got blocked, okay, the moment LED red got blocked by the delay function, I can now transition the green task to the run state. Why? Because the run state is now free. Okay, the moment the LED red goes to the block state, the LED green is now able to transition from the ready to the run. So when that happens, this LED green will go and switch on the green LED, okay, and then have a delay. Okay, so as you can see, what happens is both LEDs remain on, okay, for that duration of 1 second. Okay, even though there is a slight delay, okay, you don't see that visibly because it's very fast. Okay, now some of you, when you run this in your lab, okay, when you run it on your board, you will see that, hey, how come it doesn't show as yellow? Okay, and in most cases, it is because of your own LED function. Okay, because I know some of you, when you implement your LED function, okay, what you do is when you switch on one LED, you make sure the rest of the LEDs are off. Okay, that is your own implementation. All right, so when you do that, what happens is your one LED, when you switch on the LED red, is fine, but when you switch on the LED green, your code automatically switches off the LED red. All right, but in my code, okay, the way I'm showing you is when I call LED on, it is on. If I want off it, I must explicitly call the LED off. All right, so that is why you see that both of them remain on over here. So around 1 second, both of them will remain on. Okay, and since I call the block here first, okay, I will come out of the block earlier, slightly earlier. When I come out of the block state, I will transition to the ready. And again, there is nobody else because the green is also blocked. So from the ready, I will go to the run. Okay, so for a short period, I will be ready, and then I'll go to the run, and then I will do the off. Okay, and then I will do the delay. And similar thing will happen over here. Okay, by the time that I finish over here, I will transition somewhere to a ready state. Okay, but maybe the red LED is running. So the moment it goes to a block state, I'll be able to transition to the run state. And when I transition to the run state over here, then I go ahead to off and then do another delay. Okay, and then the whole thing just keeps repeating. All right, so that is how these two tasks are actually working, all right, to make sure that both the LEDs are on and off around the same time. Okay, so like I said, visibly you look at it as on and off together. Okay, but actually there's a very, very small fraction of time where the red LED switches on first, but then after a while the green switches off. Okay, but of course in terms of observation, we just say that we observe it as yellow blinking or red and green blinking together at the same time. Okay, so that is basically what is happening over here. All right, and of course the whole thing makes sense because we know that when I call OS delay, I go to a block state, and when I go to a block state, I'm able to free up the CPU, and the next task that is in the ready queue will be able to come in and take over. Okay, so the understanding and what we observe makes sense. All right, so we can sort of relate it together. So when I add more tasks, okay, if I add a blue thread, blue LED red thread or something else, then it just adds on to more tasks, and again the dynamics of the system. Okay, now there's just one more thing that I want to show before I end for today. All right, so that is this delay over here. Now what I'm going to do is, instead of using OS delay, I'm going to call this delay. Okay, this delay is basically what you have been using all the while. It is a standard while loop delay. So it is not putting the task in a block state or whatever. You're still going to be executing, you're still going to be running the code. Okay, still going to be running the code. Okay, so I'm going to use this delay right now instead of using the OS delay. Okay, so for both the LED red and LED green, I'm going to do that. Okay, so before we look at what's going to happen, let me run the poll one more time. Okay, to see what you feel will happen. Okay, so it's the same code. Only thing is now, instead of OS delay, I'm calling a standard sort of while loop delay, which means I'm going to be executing code, okay, while I'm still running. Okay, so what do you think will be the observation? Okay, so let's look at what's going to happen. So it's a mix of responses. All right, so some feel that it will be stuck at the red LED only. Okay, some feel it's still the same as before, and something it will be red followed by green, and then red, green, and so on. Okay, so okay, I mean all are interesting responses. So let's look at what is going to happen now. Okay, let's look at what's going to happen now. Okay, so let me compile this code first. Okay, so now we have changed it. So you can see that instead of OS delay, I'm using the actual while loop delay. Okay, so I just put some random number here on it. Okay, 0x8000. Just assume that that is equivalent to 1 second. Okay. Okay, and I'm going to run it now. Okay, you see that it is still yellow. It is still yellow. The rate is of course a bit different because it's not exactly 1000. Okay, but it is still yellow. That means I'm still seeing it as red and green lighted up together. Okay, red and green lighting up together. Okay, and this sort of doesn't make sense, right? Doesn't make sense because from what we just discussed, okay, if my current task is running, okay, I can only have this transition when I go to a block state. And since I am now calling delay, which is the loop delay and not OS delay, how is it still possible for me to transition? By right, I should be stuck here forever. Okay, I should be stuck here forever. All right, so why is it I'm still able to transition from LED red to LED green? All right, so that comes back to something else. Okay, that means there's something else that is happening. All right, and what is it that is happening that allows this transition to happen? Okay, so this is again something that I would say is OS dependent. Okay, some OS may implement this, some may not implement it. Okay, in our RTX RTOS, okay, if you look under RTX config, there is actually this flag that is set by default, which says that OS Robin enable. Okay, so what it does, it actually does this round robin thread switching, okay, every 5 ticks, okay, for tasks that are of equal priority. Okay, so even though, okay, there is no explicit function call or event that makes a task go to a block state, since both of them are created with the same equal priority, okay, that means every 5 ticks, okay, or every 5 milliseconds or so, you can say that whatever happens, I will still allow a transition from one task to another task, okay, between all the tasks of equal priority. So that is why, even though I'm using my actual loop delay function, I'm still able to transition over to LED green and still get it to switch on and switch off and everything. Okay, so this is again something unique, okay, and I think it's a very useful feature to have because it actually allows you to create tasks that are considered equal without worrying about how to manage between them, because the OS already automatically does this round robin for us. Okay, so as long as the tasks are equal priority, the OS itself will do a round robin to make sure that they have equal access to the CPU. Okay, so again, this is something interesting, and when you run the lab, okay, please go and try it out, you know, and see it for yourself. Okay, what happens when I enable, when I disable, and so on. All right, so that sort of wraps up, okay, today's class. Okay, so I hope that, you know, by going through this lab demo, you sort of have a much better idea on how everything comes together. All right, and you are able to sort of relate to what you're going to observe in the lab, okay, with what I've explained here. All right, so yeah, so this week's lab is you're supposed to make sure that the OS is loaded correctly and you're able to run this. Okay, and of course, at the same time, please continue to work on your hardware and your project and try to catch up with things. Okay, so that's all I have. Thank you very much. Okay, if you have any questions, you can stay back and ask me. Okay, if not, I'll see you all next week.